Most power outages caused by lightning could be avoided. Of course, if the right surge protection devices were in place. And yet, one solution for overhead lines remains largely overlooked: externally gapped line arresters, EGLAs or EGLAs. Today, I am at the Siemens Energy High Voltage Test Lab in Berlin, Germany, where we will dive into the key principle of EGLAs, how they work, how they are tested, and how they can make a critical difference for unshielded distribution line. Because we will also take you behind the scene of a unique distribution line project that puts this technology to the test, quite literally. My name is Florent Giraudet. I am an independent consultant, have spent the last 15 years working at the intersection of surge protection and lighting performance for power system. Okay, let's get started. Lightning is not just a force of nature. For power utilities, it's one of the leading causes of line outages and equipment failure. A single strike can trigger a cascade of issues: costly service interruptions, financial penalties due to regulatory non-compliance, increased maintenance and repair demands, and above all, safety risk for workers and the public. In many cases, this problem are the result of lightning-induced flashovers on line installations, especially in areas where shielding or conventional protection methods are difficult to implement. This is where line surge arresters, or LSAs, they come in. LSAs provide a cost-effective and flexible solution for improving lighting performance, particularly on overhead lines that are otherwise vulnerable. By safely diverting lightning current to ground, they prevent flashovers and help maintain service continuity, even during serious storms. But installing LSA is not just about adding hardware, it's about making sure the device itself is reliable, properly dimensioned, and does not introduce new risk over time. Among the available options, externally gapped line arresters have proven especially effective. Thanks to their robust design, field-tested performance, and cost efficiency, EGLAs have become a preferred solution for many utilities seeking to reduce lightning-related outages without overhauling the entire networks. Externally gapped line arresters, or EGLAs, are engineered specifically to prevent lightning-induced flashovers on overhead line installation. Unlike surge arresters used in substations, which are typically gapless and protect critical assets like power transformers, EGLAs are optimized for overhead transmission and distribution lines, especially where cost, simplicity, and maintenance-free operation are essential. At the heart of an EGLA is the series varistor unit, or SVU, a stack of metal oxide varistors, or MOVs, designed not to only divert energy to ground, but also to interrupt follow current after a lightning event. The system includes a spark gap. This gap is carefully dimensioned and tested so that it will always spark over during a lightning impulse, but not during normal operating voltage. Once the flashover occurs, the lightning discharge current is safely diverted to ground through the MOVs. But what happens next is just as important. After the impulse, the air becomes ionized and the power frequency follow current tends to flow. The MOV stack must then interrupt this current, and it does so typically within half a cycle, extinguishing the arc and restoring insulation integrity. For EGLAs to operate reliably over time, especially on unshielded lines or in regions with high lightning activity, proper dimensioning of the MOV is critical. That means selecting a metal oxide varistor with the right energy handling capability based on expected charge transfer and lightning severity in the area. In this factory acceptance test, we'll be testing several EGLAs manufactured by Siemens Energy, a company with more than 100 years of experience in the design and production of surge arresters. Across a century of innovation, Siemens Energy has established itself as one of the largest global manufacturers in this field. Their expertise covers the full spectrum of surge arrestor technologies used in today's power systems. The company operates two dedicated production facilities, one in Berlin, Germany, and one in Wuxi, China. These factories specialize in the manufacturing of surge arresters and composite insulators, supporting worldwide demand and ensuring consistent quality across all voltage levels. Siemens Energy offers a broad application portfolio, supplying surge arresters for substation, overhead lines, HVDC system, GIS installation, railway networks, and distribution system. This range allows utilities and manufacturers to select optimized solution for virtually any network configuration. For transmission lines, Siemens Energy provides line surge arresters and insulators up to 765 kV, designed for high-performance operation under demanding electrical and environmental conditions. They are also a major contributor to externally gapped line arresters. Their EGLAs product line can also include the wall assembly, the arrestor unit, the SVU, the insulator, and all associated hardware. Again, available up to 765 kV. Not all EGLAs are created equal. To gain full confidence in the performance, end users need assurance, not just in the product itself, but in the entire chain, from design and dimensioning to manufacturing quality, testing, and proper integration on the line. One of the most critical aspects when selecting an EGLA for overhead lines is insulation coordination, ensuring that the surge arrestor protects the system without causing unintended flashovers. As we saw earlier, EGLAs are built around an external spark gap, as you can see here. This means the protection level is defined by the sparkover voltage of the complete EGLA, not directly by the result voltage of the SVU. But it's not just about one number. To ensure reliability, statistical dispersion, timing margins, and installation tolerances must be all taken into account. The IC 699-8, the international standard for EGLAs, defines a minimum protective margin to ensure the EGLA sparks at the right place and not somewhere else on the insulator. That's why the factory acceptance test, or FAT, is such an important milestone. It's the moment where the manufacturer proves in front of the client that the device meets the required system voltage, sparkover behavior, and insulation coordination targets. And that's exactly what we are going to demonstrate here today. Hi Bata, hi Mehmet, nice to meet you. It's a pleasure to have you here in the test lab for this FAT. So as part of ADM, a distribution system operator, you're operating a 36 kV unshielded line.
Correct.
And as we know, unshielded lines can be heavily affected by lightning, especially by shielding failures, so direct lightning on the phase conductors.
Correct.
And without any specific surge protection, this could be actually a big challenge for the system operator to deal with these severe lightning activities.
Correct.
So you have decided to implement EGLA, externally gapped line arresters. Can you tell us a few words about your decision process and how did you decide about that technology over alternative mitigation methods?
Thanks, Florent. Obviously, this project kicked off as a result of in the same region transmission system operator implemented. Therefore, that gave us some sort of confidence. As you correctly saying, the southwest of region of Turkey is obviously receiving a lots of lightning events. Not only the lightning density, but also the amplitude of the lightning current is quite noticeable. Therefore, as a point of continuity of supply rather than protecting the equipment, we have chosen this application EGLA. So that gave to distribution system operator a confidence to apply and take it and further application into medium voltage line. This line is about 33 kV. So therefore, the implementation of the EGLA will give us a further confidence, not only the maintenance advantages such as maintenance-free, installation EGLAs is easier than NEGLAs, non-gapped surge arresters, and also the cost of it will be the advantages. Plus, then there will be a less maintenance cost because the surge arrestor will not be energized continuously. So therefore, it will give us some sort of opportunity to enlarge the project in the future.
Okay, thank you.
Thank you.
Let's dive deeper into the EGLA insulation coordination concept. If this topic creates confusion in your project, you are not alone. At first, it's essential to clarify terminology to properly understand Western voltages related to surge arresters and especially EGLAs, where most misunderstandings begin. Several different Western voltages must be verified and coordinated, as they serve different purposes. According to IC standards, especially IC 671-1, the standard Western voltage rating for a 36 kV system, or 70 kV for the power frequency Western voltage, and 170 kV for lightning impulse Western voltage, also called BIL for basic insulation level. These Western voltage levels are conservative by design, but they always depend on the protection level of the surge arresters used in the system. In addition, if the line is installed at an altitude above 1000 meters, insulators with higher insulation level must be selected because air provides lower dielectrical strength at higher altitudes. Next, we need to look at the Western voltage of the SVU, the arrestor unit of the EGLA. In the case of a lightning discharge, we don't want the SVU housing to flash over, since one of its primary functions is of course to protect itself. The housing Western level of the SVU are defined in IC 699-8 and in the upcoming IC IEEE 699-11. These Western levels are governed by the result voltage, URS, of the MOV stack and must not be confused with the system insulation Western levels previously described from IC 671-1. Typically, the lightning impulse Western voltage of the housing should be higher than or equal to 1.3 times the residual voltage, URS, at nominal discharge current, or higher than or equal to 1.13 times the residual voltage, URS, at high current impulse. By the way, if you would like to learn more about metal oxide varistors, MOVs, their manufacturing process and basic fundamentals, we encourage you to watch our dedicated video on this topic. You can find the link in the description. Now, back to insulation coordination. The rule is simple, but absolutely critical. The external series gap of the EGLA should always spark over before the line insulation flashes over. In physical terms, this means that the EGLA protection level, UPL, must be less than or equal to the coordinated lightning impulse Western voltage of the line insulation. The protection level, UPL, of an EGLA is governed by its sparkover behavior, which is mainly influenced by the gap distance and the stray capacitances of the SVU. This coordinated lightning impulse Western voltage is derived from the statistical lightning impulse flashover characteristic of the line insulation, including the selected standard deviation and the associated safety factor. During EGLA acceptance testing, one key objective is to verify this insulation coordination. This requires determining U50 of the EGLA and U50 of the line insulation. By applying the appropriate statistical deviation and safety factor, the protection margin can then be defined and verified through testing. Finally, once the maximum gap distance has been determined ensuring that the EGLA sparks over only under lightning impulses. The minimum gap distance must also be established. This minimum distance ensures that the gap can withstand the switching impulses under wet condition and the power frequency withstand voltages also under wet condition. This step is particularly critical in distribution system where it's necessary to estimate the prospective switching surge factor and the maximum temporary overvoltage, TOV. In other words, EGLA dimensioning often challenges conventional insulation distances and must therefore be approached with care, physics-based reasoning, and proper coordination. A reliable failure rate analysis goes beyond ticking off rating boxes. It should be part of a life cycle cost strategy, combining probabilistic studies with the result from statistical testing. As we discussed earlier, direct lightning strikes to phase conductor on unshielded lines pose a serious challenge. In these cases, it's critical to review carefully the dimensioning of the MOV blocks used in EGLAs. Unfortunately, this topic is often overlooked, largely due to the lack of established methodologies and simulation tools. The use of conventional distribution class arresters has shown clear limitation in this context. The key question is, what methodology should we use to define meaningful reliability metrics based on severe lightning events? For this project, we used the SIGMA SLP software to simulate the expected failure rate on MO-based line surge arresters. Failure is defined here as any case where the charge transfer from lightning exceeds the EGLA nominal QRS ratings. Factors like stroke current distribution and ground flash density, GFD or NG, heavily influence the outcome. From a system perspective, lightning exposure varies by phase. And in this project, for example, it was decided to apply larger MOV EGLAs only to the top phases, while standard distribution class type EGLA were used on the middle and the bottom phases, where shielding failures are less critical. To predict failure rates accurately, we correlate the QRS rating, the statistically verified repetitive charge transfer capability of the MOV, which is tested under 200 microseconds, current waveform, with simulated lightning charge transfers calculated by SIGMA SLP. These simulations rely on the combination of the electro-geometric model in EGM, the Monte Carlo method, and real-world lightning data. The result is a more informed, data-driven approach to dimensioning and validating EGLA solution, with a clear focus on long-term reliability under lightning conditions. Lightning performance on overhead line is not a theoretical problem. It's an operational, economic, and reliability challenge faced by utilities worldwide. In this video, we have seen that externally gapped line arresters are not just another protection device. When they are properly dimensioned, tested, and coordinated, they can dramatically reduce lightning-related outages, even on unshielded lines, without compromising long-term reliability. We have also seen that EGLA's performance is not defined by a single rating or a catalog value. It's the result of an insulation coordination, sparkover behavior, MOV charge capability, and system-specific lightning exposure, all working together. And this brings me to why this video matters. From the utility side, there is often room to go deeper into IC standards, not just to comply with them, but to use them intelligently to build specifications that truly reflect the needs of the network. From the manufacturer's side, there is also an opportunity to better align designs, testing philosophies, and dimensioning approaches with real-world system conditions. Medium voltage applications are a perfect example of this gap and also of the opportunity. Externally gapped line arresters have existed for nearly 4 decades, yet we firmly believe their full potential is still far from being realized, especially on distribution line exposed to severe lightning conditions. With better understanding, better coordination, and better dialogue between users and manufacturers, EGLAs have a bright future ahead as a reliable, cost-effective, and technically sound solution for improving lighting performance. Thank you for watching, and don't forget to subscribe to support our work. If you need support with surge technology, installation coordination, or lighting performance, this is exactly what we do. We work with power utilities, consulting companies, contractors, and manufacturers to translate standards, physics, and real-world data into practical, reliable solutions. If you would like to discuss a specific project or challenge, feel free to reach out. You can book a call directly via the link in the description.